Good day, everyone. This is Natalie Joy G. Morales, and I'm going to discuss about Chapter 6, Clusters and Group of Galaxies. Galaxies are not uniformly distributed in space, but instead show a tendency to gather together in galaxy groups and clusters of galaxies. The transition between groups and clusters of galaxies is smooth. Historically, the distinction was made on the basis of number of their member galaxies. Clusters of galaxies are very massive. Typical values are m is greater than or approximately 3 times 10 to the 14 molar masses for massive clusters, whereas for groups, m approximately 3 times 10 to the 13 molar masses is characteristic with the total mass range of groups and clusters extending over m is greater than or approximately 10 to the 12 molar masses and less than or approximately few times 10 to the 15 molar masses. The Milky Way itself is a member of a group called the local group, which implies that we are living in a locally overdense region of the universe. And we have here the figure, the distribution of galaxies in the northern sky as compiled in the Leak catalog. This catalog contains the galaxy number counts of pixels of 10 by 10 prime by 10 prime each. It is clearly seen that the distribution of galaxies on the sphere is far from being homogeneous. Instead, it is distinctly structured. So we can see the distribution of all galaxies brighter than B is less than 14.5 on the sphere, plotted in the galactic coordinates. The zone of the avoidance is clearly seen as the region near the galactic plane. So we have an example of a group and a cluster of galaxies here in this figure, and it shows the HCG40, a compact group of galaxies observed with the Subaru telescope on Mauna Kea. And we have here the figure of cluster of galaxies CI005337 observed with the WFI at the ISO or /MPG 2.2 meter telescope. The local group. The Milky Way is a member of local group within a distance of approximately 1 MPC around our galaxy, and about 35 galaxies are known at the turn of the millennium. These classical local group members are listed in the next slide, in the table next slide, and with SDSS about 20 additional very faint galaxies in the local group have been found. And so we have here listed are the name of the galaxy, its morphological type, the absolute B-band magnitude, its position on the sphere in both right ascension or declination and in galactic coordinates, its distance from the sun and its radial velocity. And we also have here the schematic distribution of galaxies in the local group with the Milky Way at the center of the figure shown are only the classical local group members which have known before 2000. Most of the newly found galaxies in the local group are ultra-faint dwarfs. Phenomenology. The Milky Way, M31 and M33 are the three spiral galaxies in the local group and also its most luminous members. The Large Magellanic Cloud is next in luminosity in the local group. Because of their low luminosity and their low surface brightness, and many of the known members of the local group were detected only fairly recently. One example is Atlia Galaxy, a dwarf spheroidal galaxy found in 1997. Its luminosity is about 10 to the 4 times smaller than that of the Milky Way. Mass estimate. M31 is one of the very few galaxies with a blue shifted spectrum. Hence, Andromeda and the Milky Way is approaching each other at relative velocity of v 120 kilometer per second. This value results from the velocity of M31 relative to the Sun of 300 km per second and from the motion of the Sun around the galactic center. The luminosity of the local group is dominated by the Milky Way and by M31, which together produce about 90% of the total luminosity. If the mass density follows the light distribution, the dynamics of the local group should also be dominated by these two galaxies. In the early phases of the universe, the galaxy and M31 were close together and both took part in the Hubble expansion. By their mutual gravitational attraction, their relative motion was decelerated until it came to halt at a time T max at which the two galaxies had their maximum separation R max from each other. So from this time on, they have been moving toward each other. The relative velocity v function of t and the separation r function of t follow from the conservation of energy. We have v squared over 2 is equal to gm over r minus c, where m is the sum of masses of the Milky Way and M31 and c is an integration constant related to the total energy of the M31 MW system. This constant can be determined by considering at the time max separation when r is equal to r max and v is equal to 0. So with this we have c is equal to gm over r max. So since v is equal to dr over dt is a differential equation for r function of t, then we have this equation, 1/2 dr over dt squared equals gm times 1 minus r minus 1 over r max. And it can be solved using the initial condition r is equal to 0 and t is equal to 0. For our purpose, an approximate consideration is sufficient. Solving the equation for dt, then we obtain by integration a relation between r max and t max. So we have this equation. And since the differential equation is symmetric with respect to changing v to negative v, the collision will happen at 2t max. So estimating the time from today of the collision by assuming the relative velocity to be constant during this time, then this yields to t max, which is approximately equal to t sub o over 2 plus d over 2v, which is approximately equal to 10 to the 10 year, where t sub o is approximately equal to 14 times 10 to the power of 9 years is the current age of the universe. Hence, this yield to v to the power of 2 over 2 equals gm over r minus gm over r max, which is equal to gm over r minus 1/2 times pi gm over t max to the power of 2 over 3. By inserting the values of r function of to equals to d and v equals v function of to, we obtain the mass m, which is approximately 3 times 10 to the power of 12 molar masses. Now we have other components of the local group. Tidal streams. is one of the most interesting galaxies in the local group is the Sagittarius dwarf galaxy, which was only discovered in 1994. Since it is located in the direction of the galactic bulge, it is barely visible on optical images, if at all, as an overdensity of stars. Therefore, it has a very low surface brightness. It was discovered in an analysis of stellar kinematics in the direction of the bulge, in which a coherent group of stars was found with a velocity distinctly different from that of bulge stars. The neighborhood of the local group. The local group is indeed a concentration of galaxies, while it contains more than 50 members within approximately 1 MPC. Sculpture group, M81 group, Centaurus group, M101 group, M66 and M96 group, and NGC 1023 group. Optical cluster searches. The Abel catalog, George Abel compiled a catalog of galaxy clusters published in 1958, in which he identified regions in the sky that show an overlay density of galaxy. And this identification was performed by eye on photoplates from the Palomar Observatory Sky Survey. A photographic atlas of the northern sky. He omitted the galactic disk region because the observation of galaxies is considerably more problematic there due to extinction and the high stellar density. Abel's criteria and his catalog. The criteria Abel applied for the identification of cluster refers to an overdensity of galaxies within a specified solid angle. According to this criteria, a cluster contains less than or equal to 50 galaxies in a magnitude interval m is greater than or equal to m sub 3 or and m less than or equal to m sub 3 plus 2, where m3 is the apparent magnitude of the third brightest galaxy in the cluster. Clusters are also classified by the morphology of their galaxy distribution. Several classifications are used, one of which we have here a figure, a rough morphological classification of clusters by Rood and Sastry. CDs are those which are dominated by a central CD galaxy. BS contains a pair of bright galaxies in the center. LS are clusters with a nearly linear alignment of the dominant galaxies. And CS have a single core of galaxies. FS are clusters with an oblate galaxy distribution, and LS are clusters with an irregular distribution. This classification has the more regular clusters at the left figure and irregular clusters at the right. And since this is a description of the visual impression of the galaxy distribution, the exact class of cluster is not of great interest. However, a rough classification can provide an idea of the state of a cluster, whether it is currently in dynamical equilibrium or whether it has been heavily distributed by a merger process with another cluster. Accumulations of galaxies that do not satisfy Abel's criteria are in most cases galaxy groups. Hence, groups are the continuation of clusters towards a fewer member galaxies and are therefore presumably of lower mass, lower velocity dispersion, and smaller extent. The distinction between groups and clusters is at least partially arbitrary, and it was defined by Abel mainly to be not too heavy affected by projection effects in the identification of clusters. And we have here a definition of Abel's richness classes, where n is the number of cluster galaxies with magnitude between m sub 3 and m sub 3 plus 2 inside Abel's radius, where m sub 3 is the brightest of the third brightest cluster galaxy. And we have the definition of Abel's distance classes, where m sub o is the magnitude of the 10th brightest cluster galaxy. Modern optical catalogs. Color magnitude diagram. Color magnitude diagram of the cluster of galaxies Abel 2390 observed with the HST. Star symbols represent early type galaxies identified by their morphology, while diamonds denote other galaxies in the field. The red cluster sequence is clearly visible. Note that due to the projection effects, not all galaxies shown here are indeed cluster members. Some of them are foreground or background galaxies. The RCS survey. The cluster red sequence method was used in several multi-band imaging surveys for the detection of clusters. In fact, one of the large imaging surveys carried out with the CFHT was the RCS survey. Its main purpose to detect clusters out to large redshifts. It covered 100 degrees squared in two filters and yielded more than 1,000 cluster and group candidates out of the redshifts larger than unity. As a follow-up, the RCS2 survey covers 900 degrees squared in the three filters and aims at detecting some 10 to the 4th clusters out to Z approximately 1. The Max BCG catalog. This cluster catalog is based on a search algorithm which makes use of three properties of a massive cluster. The first is the already mentioned red cluster sequence, the homogeneous color of early type galaxies in clusters. Second, most massive clusters are found to have a dominant central galaxy, the brightest cluster galaxy, whose luminosity can be several times larger than the second brightest cluster member. And the third property relates to the radial density profile of galaxies, which in a first approximation decreases roughly as 1 over theta from the center to the outside. And we have here the example of the two clusters found by the Max BCG method. Shown are the color magnitude relation of galaxies in the field of Abel 2142 at z equals 0.092, which is the figure at the top, and the Abel 1682 at z equals 0.23, the figure bottom. Light distribution and cluster dynamics. Spatial distribution of galaxies. Most regular clusters have a centrally condensed number density distribution of clustered galaxies. The galaxy density increases strongly toward the center. If the cluster is not very elongated, this density distribution can be assumed to a first approximation as being spherically symmetric. Only the projected density distribution and function of R is observable. This is related to the three-dimensional number density and function of R through this equation and function of R. And wherein the second step is a simple transformation of the integration variable from the line of sight coordinates r3 to the three-dimensional radius r, which is r squared plus r3 squared was made. And of course, no function and function of r can be observed, but only the points, the position of the galaxies that are distributed in a certain way. And if the number of density of galaxies is sufficiently large, so n function of r is obtained by smoothing the point distribution. Alternatively, one considers parameterized form of n function of r and fits the parameters to the observed galaxy position. Isothermal distributions. These models are based on the assumption that the velocity distribution of the massive particle of a cluster is locally described by a Maxwell distribution. They are thermalized, as shown from spectroscopy analysis of the distribution of the radial velocities of clustered galaxies. This is not a bad assumption, assuming in addition that the mass profile of the cluster follows that of the galaxies, or vice versa, and that the temperature of the distribution does not depend on the radius, so that one has an isothermal distribution of galaxies, then one obtains a one parameter set of models, the so-called isothermal spheres. This can be described physically as follows. So in dynamical equilibrium, the pressure gradient must be equal to the gravitational acceleration, so that we have this first equation, number one equation in the slide, dp over dr, and where rho function of r denotes the density of the distribution, the density of galaxies, and the mass density is related to the number density and function of r, where the mean mass is the average particle mass. So the m function of r is equal, the m function of r is the mass of the cluster enclosed with a radius r. So by differentiation, we obtain equation number 2, and the relation between pressure and density is P is equal to N K sub B and T. On the other hand, the temperature is related to the velocity dispersion of the particles, so we have here the equation 3, where the mean of v squared is the mean squared velocity. The velocity dispersion provided the average velocity vector is set to 0. So the latter assumption means that the cluster does not rotate or contract or expand. If t, or the mean squared velocity, is independent of r, then we have this equation number 4, where sigma sub v squared is the one-dimensional velocity dispersion, and the velocity dispersion along the line of sight, which can be measured from the redshift of clustered galaxies. If the velocity distribution corresponds to an isotropic distribution, the one-dimensional velocity dispersion is exactly 1/3 times the three-dimensional velocity dispersion. And we have here the fifth equation. Then it follows that we have now the final equation, d over dr, in times sigma sub v squared r squared over rho d rho over dr plus 4 pi gr squared rho equals 0. Singular isothermal sphere. For general boundary condition, the differential equation for rho function of R cannot be solved analytically. However, one particular analytical solution of the differential equation exists. It's by substitution we can easily show that we have here the first equation, rho function of R is equal to sigma v squared over 2 pi gr squared. And this density distribution is called singular isothermal sphere, and we have encountered this distribution has a diverging density as R approaching zero and an infinite total mass of m function of R, which is inversely proportional to R. So this divergence of the density toward the center may not appear reasonable, and thus one might search solution with a more physical boundary condition with rho function of 0, which is equal to rho sub O or rho sub 0. The central density the density profile to be flat at the center. So numerical solution with this boundary condition reveal that the central density and the core radius are related to each other by this equation. Rho naught is equal to 9 sigma sub v squared over 4 pi g r sub c squared. Hence, this physical solution avoid the infinite density of singular isothermal sphere, and so they have a diverging mass as well. The origin of this mass divergence is easily understood because this isothermal distribution are based on the assumption that the velocity distribution is isothermal, thus Maxwellian with a spatially constant temperature. King's model. To remove the problem of diverging total mass, self-gravitating dynamical models with an upper cutoff and the velocity distribution of their constituent particles are introduced. These are called King models and cannot be expressed analytically. However, an analytical approximation exists for the central region of these mass profiles. With this equation, rho function of R. The analytical fit, and then from this we obtain from the projected surface mass density with this equation 2. This analytical model have the density distribution galaxies in the cluster are only approximation because the galaxy distribution in cluster is often heavily structured. Furthermore, these dynamical models are applicable to a galaxy distribution only if the galaxy number density follows the matter density. Dynamical mass of clusters. The previous argument relates the velocity distribution of cluster galaxies to the mass profile of the cluster, and from this we obtain physical models for the density distribution. This implies the possibility of deriving the mass or the mass profile respectively for a cluster from the observed velocity of clustered galaxies. We will briefly present this method of mass determination here. For this, we consider the dynamical timescale of clusters, defined as the time a typical galaxy needs to traverse the cluster once. So we have the first equation where a one-dimensional velocity dispersion sigma sub v, which is approximately 1000 km per second, was assumed. So the dynamical timescale is shorter than the age of the universe. One therefore concludes that the cluster of galaxies are gravitationally bound system. If this were not the case, they would dissolve on a timescale t sub cross. Since t sub cross is very less than to t sub 0, one assumes a viral equilibrium. Hence that the virial theorem applies, so that in a time average sense, we have here the equation 2, which is 2E kinetic energy plus potential energy is equal to 0, where the kinetic and potential energy of the cluster galaxies given in this equation 3. So mi is the mass of the ith galaxy, and v sub I is the absolute value of its velocity, and r sub ij is the spatial separation between the ith and the jth galaxy. The factor 1/2 in the definition of E potential occurs since each pair of galaxies occurs twice in the sum. So in writing this, we have assumed that the total mass of the cluster is the sum of all its member galaxies. So given this equation 4. This assumption is not valid, since we will find below most of the cluster mass is not contained in galaxy. However, if we assume that the total mass is distributed in the same way as the galaxies are, we can associate to each galaxy a representative mass, so that the superposition of all these representative masses yields the total mass distribution of the cluster. So the mass mi used in the foregoing equation and below is meant to be this representative mass. So we further define the velocity dispersion weight by mass here given in this equation number 5, and the gravitational wedges, which is we can see here in equation number 6. So with this, we obtain equation number 7, the E kinetic and the E potential. Applying the virial theorem, so we came up with the mass estimate with this equation number 8. M is equal to R G square velocity, mean square velocity, v squared velocity, and over G. Transition to projected quantities. The previous derivation uses the three-dimensional separation Ri of the galaxies from the cluster center, which are however not observable. To be able to apply these equations to observation, they need to be transformed to projected separations. If the galaxy position and the direction of the velocity vectors are uncorrelated, it is the case for an isotropic velocity distribution. Then we have this equation, the mean square velocity is equal to 3 sigma sub v squared, and where we have rg is equal to pi over 2 times rg, with rg is equal to 2 m squared, and the summation of mi mg over r sub ig to the -1, where I is not equal to g. And so we're R sub ij denotes the projected separation between the galaxies I and G. The parameters sigma sub v and rg are direct observables. Thus, the total mass of the cluster can be determined and can be obtained by this equation. M is equal to 3 pi rg sigma sub v squared over 2g, which is equal to 1.1 times 10 to the 15 molar masses times sigma sub v over 1000 km per second squared times rg over 1 mpc. So we explicitly point out that this mass estimate no longer depends on the mass mi of the individual galaxies. Rather, the galaxies are now test particles in the gravitational potential, with sigma sub v approximately 1000 km per second and rj approximately 1 mpc as typical values of rich clusters of galaxies. So one obtains a characteristic mass of approximately 10 to the 15 molar masses for rich clusters. The missing mass problem in clusters of galaxies. With the mass m and the number n of galaxies, one can now derive a characteristic mass m is equal to m over n for the luminous galaxies. This mass is found to be very high, where m is approximately 10 to the 13 molar masses. And alternatively, m can be compared with the total optical luminosity of cluster galaxies, L total approximately 10 to the 12 to 10 to the 13th solar luminosity. Hence, the mass to light ratio can be calculated typically with this equation, m over L total approximately 300 h times molar mass over solar luminosity. And this value exceeds the m over L ratio of early type galaxies by at least a factor of 10. And from an analysis of the Gamma cluster, the cluster of galaxies must contain considerably more mass than is visible in galaxies, the dawn of the missing mass problem, as we will as we observed luminosity and estimated mass has by now been firmly established, since other method for the mass determination of cluster also yield comparable values and indicate that a major fraction of mass in the galaxy clusters consists of dark matter, and the stars visible in galaxies contribute less than about 5% to the total mass in cluster of galaxies. Intergalactic stars in cluster of galaxies. The space between the galaxies in a cluster is filled with hot gas and visible from X-ray observations. Beside this hot gas, there are also stars in between the galaxies. This intracluster light is the most recently discovered component in clusters. The detection of such an intergalactic stellar population comes as a surprise at first, because our understanding of star formation implies that they can only form in the dense center of molecular clouds. Hence, one expects that stars cannot form in intergalactic space. That is not necessarily implied by the presence of intergalactic stars. However, since they can also be stripped from galaxies in the course of gravitational interactions between galaxies in the cluster, or the stripping of stars from the other parts of the galaxies in the tidal gravitational field in the central region of the cluster, and so form an intergalactic population. The fate of these stars is thus somewhat similar to that of the interstellar medium, which is metal enriched by the process of the stellar evolution in galaxies before it is removed from these galaxies and become part of the intergalactic medium in the clusters. Otherwise, the substantial metallicity of the ICM could not be explained. This interpretation is strengthened by the fact that a diffuse optical light component is also seen in compact galaxy groups where the strength of tidal interaction is stronger than in clusters. Hot gas in galaxy clusters. One of the most important discoveries of the UHURO X-ray satellite, which is launched in 1970, was the detection of X-ray radiation from massive clusters of galaxies. With the later Einstein X-ray satellite and more recently ROSAT, X-ray emission was also detected from lower mass clusters and groups. We have here three examples from the X-ray emission of galaxy clusters. We have here the first figure is an X-ray image of the Coma cluster taken with a ROSAT. Um, the the image size is 2.7 degree by 2.5 degree, much larger than the optical image. A remarkable feature is secondary maximum in the X-ray emission at the lower right of the cluster center, which shows that even Kalma, long considered to be a regular cluster, is not completely an equilibrium state, but is dynamically evolving, presumably by the accretion of a galaxy group. And we have the second figure, RxJ 13471145 is one of the most luminous galaxy clusters in the X-ray domain. A color-coded ROSAT HRI image of this cluster shows the distribution of intergalactic gas, is supposed on an optical image of the cluster with redshift z is equal to 0.45. As we can see, there's two arrows which indicate the giant arcs image of background galaxies, which are strongly distorted by the gravitational lens effect. And for the last figure is the cluster of galaxies MS 105403 is at z equals 0.83, the highest redshift cluster in the Einstein Medium Sensitivity Survey, which was compiled from observations with the Einstein satellite. So, general properties of the X-ray radiation. Clusters of galaxies are the brightest extragalactic X-ray sources besides AGNs. If an X-ray telescope is pointed away from the galactic disk, about 85% of the detected sources are AGNs, and the remaining approximately 15% are clusters. So in contrast to AGNs, for which the X-ray emission is essentially point-like, the X-ray emission of cluster is extended. Continuum radiation. The spectral energy distribution of the X-ray leads to the conclusion that the emission process is optically thin thermal Bremsstrahlung free radiation from a hot gas, which is collisionally ionized. This radiation is produced by the acceleration of electrons in the Coulomb field of protons and atomic nuclei. Since an accelerated electrically charged particle emits radiation, such scattering processes between electrons and protons is an ionized gas yields emission of protons. Whereas for the line emission, the assumption that the X-ray emission originates from a hot diffused gas intercluster medium was confirmed by the discovery of line emission in the X-ray spectrum of clusters. One of the most prominent lines in massive cluster is located at energies just below 7 electrovolts. It is the Lyman alpha line of 25-fold ionized iron, and slightly less ionized iron has a strong transition of somewhat lower energies of E approximately 6.4 kilo electrovolts. Cooling flows. Expected consequence of gas cooling. In examining the intergalactic medium, we assumed hydrostatic equilibrium, but we disregarded the fact that the gas cools by its emission and by that loses internal energy. So for this reason, once established, a hydrostatic equilibrium in principle cannot be maintained over arbitrarily long times. To decide whether this gas cooling is important for the dynamics of the system, the cooling time scale needs to be considered. This cooling time turns out to be very long. With this equation T cool, where U is equal to 3 halves in case of B, and times T sub G is the energy density of the gas, and the n number of Ne, the electron density. So hence the cooling time is longer than the Hubble time nearly everywhere in the cluster, which allows a hydrostatic equilibrium to be established to a very good approximation. In the center of clusters, however, the density may be sufficiently large to yield T sub 0 is greater than or approximately T cool and approximately to H sub 0 to the negative 1. So here the gas can cool quite efficiently, by which its pressure decreases. This then implies that, at least close to the center, the hydrostatic equilibrium can no longer be maintained. To re-establish pressure equilibrium, gas needs to flow inward, and is thus compressed. Hence, an inward directed mass flow should establish itself. The corresponding density increases will further accelerate the cooling process. The fate of the cooling gas. The gas cooling in this way will accumulate in the center of the cluster, but despite the expected high mass of cold gas, no clear evidence has been found for it. In clusters harboring a CD galaxy, the cooled gas may, over a Hubble time, contribute a corresponding fraction of the mass of this galaxy. The gas would be transformed into stars in the CD galaxy, and however, the star formation rate in these central galaxies is much lower than the rate. Radio relics. In some galaxy clusters, one finds extended diffuse radio sources at large cluster-centric radii. The so-called radio relics, these radio sources do not coincide with member galaxies in the cluster, and thus have an intercluster origin. Their shapes are often very elongated or irregular, as can be seen by the example figure here, a 1.4 GHz map of the galaxy cluster CISA J2242.8 plus 5301 at redshift z equals 0.1921. Taken with the Westerbork synthesis radio telescope, on which the X-ray contours, shown in red, are the superposed. The most prominent radio source is the large elongated features, some 1.5 mpc to the north of the cluster center, whose length is approximately 2 mpc. The strong polarization of the radio emissions shows that the origin of the radiation is synchrotron emission. Therefore, these radio relics must contain relativistic electrons, about 50 radio relics have been found to date. Scaling relations for clusters of galaxies. Our examination of galaxies revealed the existence of various scaling relations. For example, the Thule-Fisher relation. These have been proven to be very useful not only for the distance determination of galaxies, but also because any successful model of galaxy evolution needs to be able to explain these empirical scaling relations. They must contain information about the formation of galaxies, and therefore it is of great interest to examine whether clusters of galaxies are also fulfill any such scaling relation. Mass temperature relation. It is expected that the larger the spatial extent, velocity dispersion of galaxies, temperature of the X-ray gas, and luminosity of a cluster are, the most massive it is. In fact, from theoretical consideration, one can deduce the existence of relation between these parameters. The X-ray temperature T specifies the thermal energy per gas particle, which should be proportional to the binding energy for a cluster in virial equilibrium. So, with the given equation 1, T is proportional to m over r. Since this relation is based on the virial theorem, r should be chosen to be the radius within which the matter of the cluster is virialized. This value for r is called the virial radius, or r sub r virial. From theoretical consideration of cluster formation, one finds that the virial radius is defined such that within a sphere of radius r virial, the average mass density of the cluster is about delta sub c, approximately equal to 200 times as high as the critical density of the universe, which is rho sub cr. The mass within r virial is called the virial mass, also denoted as mv in equation 2, according to this definition. So we have here the equation 2, mass virial is equal to 4 pi over 3 delta sub c rho sub cr and r virial cube. So combining the two relations, equation 1 and combining equation 1 and equation 2, we came up with the equation 3. This relation can now be observationally tested by using a sample of galaxy clusters with known temperature and with mass determined by the methods discussed before. And since it is easier to determine the mass inside a smaller radius than the virial mass itself, the mass m sub 500 within the radius of r sub 500, the radius within which the average density is 500 times the critical density is plotted here. So the measure values clearly show a very strong correlation, and the best fit straight line describing power law of the form m equals at to the power of alpha. So if one confines the sample of clusters within m is greater than or equal to 5 times 10 to the 13 molar masses, the best fit is described by equation 4, with an uncertainty in the parameters of slightly more than 10%. So this relation is very similar to the one deduced from our theoretical consideration. M is inversely proportional to T to the power of 1.5. Mass velocity dispersion relation. The velocity dispersion of the galaxies in a cluster also can be related to the mass. And we find equation 1, which is mass varial equals to 3r subvarial sigma sub v squared over g, and together with t, which is proportional to sigma sub v squared, and t proportional to r varial squared, it then follows that m varial is proportional to sigma sub v cubed. And this relation can be tested using clusters for which the mass was determined using the X-ray method, and for which measurements of the velocity dispersion of the cluster galaxies are available. And alternatively, the relation T proportional to sigma v squared can be tested. One finds that this relation are essentially satisfied for the observed cluster. Mass luminosity relation. The total X-ray luminosity that is emitted via Bremsstrahlung is proportional to the squared gas density and the gas volume. Hence, it should behave as as equation 1, and estimating the gas density through rho sub g approximately m m sub g r variable to the negative cube to the negative 3, which denotes the fraction with respect to the total mass of the cluster. And using cluster, so we obtain equation 2, and this relation needs to be modified if the X-ray luminosity is measured within a fixed energy interval. Hence, one expects a modified scaling relation between the X-ray luminosity and the mass of the cluster. We have here equation 3, where this scaling relation can also be tested empirically, where the X-ray luminosity and the energy range of the Rosat satellite is plotted against the virial mass. And one can immediately see that clusters of galaxies indeed show a strong correlation between luminosity and mass, but with a clearly larger scatter than in the mass-temperature relation. Therefore, the temperature of the intergalactic gas is a better mass indicator than the X-ray luminosity of the velocity dispersion of the cluster galaxy. Near-infrared luminosity as mass indicator. Whereas the optical luminosity of galaxies depends not only on the mass of the stars, but also on the star formation history. The near-infrared light is much less dependent on the latter. As we have discussed before, the near-infrared luminosity is thus quite a reliable measure of the total mass in stars. For this reason, we would expect that the near-infrared luminosity of a cluster is tightly correlated with its total stellar mass. Furthermore, if the latter is closely related to the total cluster mass, as would be the case if the stellar mass is fixed fraction of the cluster's total mass, so the near-infrared luminosity can be used to estimate the masses of clusters. One selects clusters of galaxies for which masses were determined by X-ray methods, and then measures the K-band luminosities of the galaxies within the cluster. We have here the figure presents the resulting mass luminosity of diagram within R500 for 93 galaxy clusters and groups, where the mass was derived from the cluster's X-ray temperatures plotted on the top axis. A surprisingly close relation between these two parameters is seen. Clusters of galaxies as gravitational lenses. Luminous arcs. In 1986, two groups independently discovered unusual stretched arc-shaped sources into cluster of galaxies at high redshift. The nature of these sources was unknown at first. They were named arcs or giant luminous arcs, which did not imply any interpretation originally. Different hypotheses for the origin of these arcs were formulated, like for instance, emission by shock fronts in the ICM originating from explosive events. All these scenarios were disproven when the spectroscopy of the arc in the cluster above 370 showed that the source is at a much higher redshift than the cluster itself. Thus, the arc is a background source subject to the gravitational lens effect of the cluster. We have here the first figure, the cluster of galaxies A370 at redshift z is equal to 0.375 is one of the first two clusters in which giant luminous arcs were found in 1986. In this HST image, the arc is clearly visible, tangentially oriented with respect to the center of the cluster, which is located roughly halfway between the two brightest cluster galaxies and curved towards the center of the cluster. And we have the second figure, the cluster of galaxies CI22440 at redshift z is equal to 0.33 is the second cluster in which an arc was discovered. Spectroscopic analysis of this arc revealed the redshift of the corresponding source at the time of discovery in 1987. It was the first normal galaxy detected at a redshift greater than 2. Lens model. The simplest mass model for a galaxy cluster as a lens is the singular isothermal sphere. Its characteristic angular scale is specified by the Einstein radius, which is the theta e. Very high magnifications and distortions of image can occur only very close to the Einstein radius. This immediately yields an essential mass estimate of a cluster by assuming that the Einstein radius is about the same as the angular separation of the arc from the center of the cluster. Since clusters of galaxies are, in general, not spherically symmetric and may show significant substructure, so that the separation of the arc from the cluster center may deviate significantly from the Einstein radius, this mass estimate is not very accurate in general. The uncertainty is presumably approximately 30%. Models with asymmetric mass distributions predict a variety of possible morphologies for the arcs and the possible position of multiple images for an elliptical lens. We can see here in the figure the distortions of the lens effect of an elliptical potential as a function of the source position. We can see the first panel shows the source itself. The second panel displays 10 position of the source in the source plane relative to the center of the lens. The solid curves show the inner and outer caustics. The remaining panels show the inner and outer critical curves and the resulting images of the source. The investigation of galaxy clusters with the gravitational lens method provides a third, completely independent method of determining cluster masses. It confirms that the mass of galaxy clusters significantly exceeds that of the visible matter in stars and in the intracluster gas. We conclude from this result that clusters of galaxies are dominated by dark matter. The weak gravitational lens effect. The principle of the weak lensing effect. We saw that the gravitational light deflection does not only deflect light beams as a whole, but also that the size and shape of light beams are distorted by differential light deflection. This differential light deflection leads to sources appearing brighter than they would be without the lens effect. The giant arcs discussed late before are a very clear example of this distortion and the corresponding magnification. With this figure, the principle of the weak gravitational lensing effect is illustrated. Due to the tidal component of the gravitational field in a cluster, the shape of the images, which appear to be ellipses, of the background galaxies get distorted, and as for arcs, the galaxy images will be aligned, on average, tangentially to the cluster center. By local averaging over the ellipticities of galaxy images, a local estimate of the tidal gravitational field can be obtained. From this estimated tidal field, the projected mass distribution can be reconstructed. Mass reconstruction of galaxy clusters. The reconstruction of the mass density of a large number of clusters became possible. The most important result of these investigations are as follows. The center of the mass distribution corresponds to the optical center of the cluster. We can see in the first figure the tidal or shear field of the cluster C10024 plus 17 is indicated by sticks whose length and direction represents the strength and orientation of the tidal gravitational field, while here on the second figure is the surface mass density is reconstructed by means of the weak gravitational lens effect. The bright galaxies in the clusters are seen to follow the matter distribution. The orientation of the isodensity contours is the same as the orientation of the light in the center of the cluster. Bullet clusters and the nature of dark matter. The mass is centered in the galaxy distributions of the two clusters and clearly displaced from the X-ray emitting gas. Therefore, the mass discrepancy cannot be ascribed to a modification of the law of gravity. Instead, the main mass component of the clusters must behave similarly as the galaxies, collisionless. Thus, the bullet cluster provides the clearest direct proof for the existence of dark matter, whereas the bullet cluster was the first of its kind. In the meantime, other cluster collisions have been investigated as well. The weak lensing results from clusters in collision cannot be explained without the existence of collision, less dark matter in galaxy clusters, even if modifications of the law of gravity on large scales were allowed for. Dark matter filaments between cluster pairs. The hierarchical structure of growth in the universe, a consequence of the cold dark matter model, predicts that mass concentrations from near the intersection points of the dark matter filaments through which they accrete mass. These filaments in general have a density too low to produce a detectable weak lensing signal. We have here the figure, the pair of clusters about 222 and 223. As observed with the Subaru telescope, the filament between the pair of clusters is clearly indicated. The galaxy population in clusters. The morphology density relation. The mixture of galaxy types in clusters seems to differ from that of isolated field galaxies, whereas about 70% of luminous field galaxies are spirals. Clusters are dominated by early type galaxies, in particular in their inner regions. The fraction of spirals in a cluster depends on the distance from the center and increases larger R. Obviously, the local density has an effect on the morphological mix of galaxies. Alternative consideration, the color density relation. We pointed out that galaxies at fixed luminosity seem to have a bimodal color distribution. The fraction of galaxies that are contained in the red population can be studied as a function of the local galaxy density. The result of the study shown in this figure. The first figure, the fraction of galaxies in the red population, is shown as a function of sigma 5, an estimator of the local galaxy number density based on the projected distance of the fifth nearest spectroscopically confirmed neighbor galaxy within plus and negative 1000 km per second. And on the second figure, the same red fraction is plotted against a combination of the local galaxy density, sigma 5, and the luminosity of the galaxy. E plus A galaxies. Galaxy clusters contain a class of galaxies which is defined in terms of spectral properties. These galaxies, which are rare in number, show strong Balmer line absorption in their spectra. Characteristic of A stars, but no or H alpha emission lines. These galaxies are not undergoing strong star formation at present, since there are no H2 regions around O and B stars. These galaxies have been termed ECA galaxy since their spectra appears like a superposition of that A stars and that of otherwise normal elliptical galaxies. They are interpreted as being post-starburst galaxies, since they were first seen in clusters. The interpretation of the origin of E plus A galaxies was originally centered on the cluster environment. Today, we're able to discover and analyze clusters of galaxies at redshift z approximately 1 and higher. Thus, the question arises whether these clusters have the same properties as the local clusters. At z approximately 1, the age of the universe is only about half of that of the current universe. One might therefore expect an evolution of cluster properties. Luminosity function. First, we shall consider the moving number density of clusters as a function of redshift, or more precisely, the evolution of the luminosity function of clusters with z. Here in figure 1, X-ray luminosity function of galaxy clusters, as was obtained from a region around the North ecliptic pole, the region with the longest exposure in the Rosat All-Sky survey. While the second figure is the luminosity derived from the flux in the photon energy, range from 0.5 to 2 kilo electric volt. The three different curves specify the local luminosity function of the clusters, as found in other cluster survey at lower redshift. We see that evolutionary effects in the luminosity function are relatively small and become visible only at high luminosity.